part of this great series. Yes, there is a robot out right now. It's actually this robot pictured behind me, if you can see that. And I'm happy that it's out there collecting data instead of me, given the weather that's been happening the last several weeks. So I'm going to talk a little bit today about the robots, mostly focusing on the applications of how it's being used in the context of offshore wind. And so I know it's certainly a hot topic in a lot of the research circles that I'm finding myself in these days. And I just wanted to share some of what I can give in terms of that background, so that you have a foundation to understand how we're using these robots to help inform how we understand offshore wind will be deployed and some of those processes. So as Caitlin mentioned, I'm a oceanographer at Rutgers. I've been at Rutgers since 1997. All of my early time at Rutgers was down at Tuckerton. It has a very special place for me, doing a lot of work off of coastal New Jersey. Since then, I've done research all over the world. I've been fortunate enough to go to Antarctica 4 different times for research projects and visit most of the world's ocean. But today I'm going to focus on our lovely coast off of New Jersey. So I'm going to share my screen so you can see some of the slides that I have. And Caitlin, is that clear? Are we good?
Yep, looks great.
Okay, perfect. So here's another picture. We have a lot of pictures of our underwater robots. It may not be a robot as you're familiar to seeing, but this is a robot that is really well equipped to navigate the ocean and collect data for us, important data on a lot of different variables and topics. I'm going to focus on the energy. And in particular, it's going to segue into offshore wind. And this is a visual that has been put together to visualize the way that we as a country have used electricity, how that electricity has been generated. So there's different sources listed there. You can see coal, natural gas, nuclear, hydroelectric, and wind. I can tell you that the yellow is solar, and I can't remember what the pink or the gray represents. But you can see how over the last 20 years, there have been some transitions. You can see some change points where coal has transitioned from 51% of our electric generation to about 23%. Nuclear stayed about the same. We do see a bump up in natural gas. And you can see, particularly in the last couple of years, some increases in both solar and wind. Most of this wind curve is based on onshore wind. The US has utilized quite a bit of onshore wind turbines, particularly out west, that are providing power. If we zoom in on New Jersey and we look at what's been happening in New Jersey, here's that same time period going from 2001 to a couple of years ago, 2019. And you can see this pretty dramatic shift that occurred around 2014, where natural gas almost doubled. Nuclear came down. This is, of course, due in large part to the Oyster Creek shutdown. And we're seeing some bump up in solar. When we think about offshore wind, this is the state's target. So the state's target is to have about half of the electricity demand in the state of New Jersey provided by offshore wind. So this is a very dramatic change. They have a plan outlined in this New Jersey offshore strategic plan that was released a couple of years ago, about a year and a half ago, about how the state can get to that target of 7.5 gigawatts by 2030. So what is offshore wind? Offshore wind is literally these turbines that are deployed in the ocean environment. Therefore, they do not occupy the land. So in terms of land use and some of the conflicts that occur there, and because they're over the ocean, they can also be built considerably larger. As of tonight, there are only 7 turbines operating in US waters. 5 of them are in Block Island state waters, Rhode Island state waters off the south coast of Block Island. These are 5 turbines that are operating, providing about 30 megawatts of energy. For perspective, that's enough energy to power the demand of Block Island and also provide some power back to the state's mainland. There are also 2 turbines that have been deployed off the coast of Virginia, and these are meant to be basically a test facility for research. Dominion Energy has put those out, and those are all of these turbines, and the ones pictured on the right are the ones off of Block Island. These are what are termed 6 megawatt turbines. So that's the size of about a 6 megawatt turbine. For some perspective, the turbines that are being proposed for some of the future farms are about twice that size. They are roughly 12 megawatt machines and about twice the size. Offshore development, while it has some of those advantages that I outlined, does face challenges that land-based don't have. One is that the ocean moves. And so the characteristics of the ocean and some of the concerns and the uses, the ocean uses, are dynamic. And there are multiple ocean uses. So trying to come up with ways in which it can be compatible with other uses is a challenge that's being faced by offshore wind in our region. Why offshore wind off the mid-Atlantic coast, in particular, off the New Jersey coast in particular? One reason is there's a lot of people here. About a quarter of the US population lives between Washington, DC and Boston, Massachusetts. And so there is a high demand for energy when you put that many people in this relatively small part of the US. This is a picture of the United States from space. So the lights there are an indicator of population density. Also for the power demand. And so in the mid-Atlantic, we have the benefit of a market that's in need of power and a high population that's requiring that power, that's in close location to the ocean environment where they're planning to build these offshore wind facilities. Another key piece, which is obviously a critical piece when we think about offshore wind, is that there are a wind resource offshore. So this is a map that's made by the National Renewable Energy Lab, part of the Department of Energy. And it indicates where on the surface of the continental US and the continental shelf that's within the US territorial waters, what the typical winds are over an annual average. And so areas that you see highlighted in red, you can see some here in the Midwest, off the West Coast and up here in the Northeast. Those are areas where the winds on average are higher, and areas where you see in purple and blue, those are areas where you typically see weaker winds. And one thing you notice in our area is that there is a good wind resource offshore. And this is not intentionally done, but you can see how dramatic the wind resource changes when you move from on-land areas to coastal areas. So it's quite an abrupt change when you move out off the beach offshore in terms of the reliability of the winds that are out there that will be available for these types of facilities. So there's that wind resource. So for these reasons, the states in the Mid-Atlantic have all made commitments to transition their power generation to offshore wind utilities. And these are some of the different targets that have been set by the individual states. You can see New Jersey there has committed 7.5 gigawatts or 7,500 megawatts of power by 2035. I understand that to be about half of the power demand for the state. You can see other states are also setting their own goals for this, and collectively for the Mid-Atlantic region, that exceeds almost, it's 39.2 gigawatts of power total. The federal government has set a goal of 30 gigawatts by 2030. And so these goals by both the states and the feds have prompted quite a bit of activity to see how these goals can be met and to do it in a way that is based on the science and what we know about the place, given some of those challenges that I've talked about. These are some of the locations that are being considered or have already been leased to companies to develop utility scale offshore wind facilities. So you can see there are a grouping of lease areas off of southern New England, south of Martha's Vineyard and Block Island and Nantucket. There are a grouping of lease areas that are off the coast of New Jersey, New York, and then down south towards Cape Hatteras. I will say that these purple areas are not yet leased, although, and I'll mention this a little bit later, these areas are scheduled to go for auction later this month. The two that have been most closely linked to activities in New Jersey are this green lease area here, which is currently leased by Ørsted North America. You can see it here. And then this maroon area up here is leased by Atlantic Shores. So at Rutgers, that's sort of the background that I wanted to give on where we are in sort of this broad scale of offshore wind. At Rutgers, we're focusing research on a lot of different aspects of this introduction of a new industry to the region. And this plot, while busy, I apologize, kind of summarizes where a lot of that work is being done. Down here in the purple, these are some of the engineering questions specific to the individual turbines, but also going up to the actual physical grid, how transmission of power will be moved, all of those important questions related to offshore wind. Up here in the green area are questions about the economics. How will this impact the individuals in the state, but also the economics of how power is generated and managed through the different markets, how the supply chain, we've heard a lot about supply chain in the recent months, a real big impact, understanding how the supply chain specific to offshore wind might work. And then this area over in the blue is where I sit, where we're thinking about what are some of those environmental research questions related to offshore wind. What is our understanding of our moving ocean, and how does that influence decisions on how offshore wind is deployed? What are impacts on some of the ecology, the marine mammals for conservation, some of the different fisheries for either conservation or recreational and commercially targeted species? What is the wind resource when we look at specific to New Jersey coastal waters? How does that change over time? How reliable can power from a wind turbine be, given what we know about that? So this is where I'm going to focus for the remainder of the talk, is in this environmental side. And I am not going to get into this in detail, but except to say that there is a very lengthy process that goes from the initial planning for a wind farm to the actual installation. And this process could take 5 to 10 or even longer years to complete. And each of these steps, there are opportunities for public comment. There are many places where environmental and ecological reviews are done, and that is where we really focus. We want to make sure that we're providing the best science, the best data on this dynamic ocean environment. And frankly, with a lot of the work that we've been doing at Rutgers and with our partners throughout the region, I'll show you we have quite a bit of information that we can provide to this process. And so I can't pretend to understand all the different steps on this diagram, and there are multiple steps within each step, but just to say that there are opportunities for public and for the science to contribute, and that's where we're focused. So this is our environment. We're going to get now to some of the oceanography and the tools. One of the real challenges facing offshore wind is thinking about how do we now plan a utility scale infrastructure off the coast of New Jersey that is proposed to be there for 25 years when we know that there are so many different complex processes that are going on in the ocean. These are a relatively meant to be more straightforward diagram to try and summarize what some of those processes are. There are physical things going on, like the winds pushing the ocean currents around, precipitation impacting how fresh the ocean surface might be, the sun and how it heats the ocean, how it fuels phytoplankton blooms at the base of the food web. That food web extends all the way up to top predators. There are interactions with the coast, river outflows. There's chemical considerations to understand when we think about our ocean environment. And so from an oceanographic perspective, this is our livelihood. We as a research community are trying to understand the complexities that are kind of shown in this plot. And in particular to offshore wind, we want to make sure what we know about these different processes that overlap with the ocean offshore wind lease areas is made known and is considered as it gets developed. And from my perspective, I am an oceanographer. And so my interest is in trying to understand I should say I'm a physical oceanographer. And so my interest is trying to understand how the ocean moves, why it moves. And in particular, I'm really interested in the particular features in the ocean that might be relevant to fish or marine mammals. So are there fronts and eddies in the ocean? And this is really important, as again, I say, we try and understand how we can take this fundamental knowledge about our dynamic ocean environment and have it inform different human uses in the ocean. So we might be able to plan better shipping or more efficient shipping of all the different goods that need to make its way around the planet. Understand how to sustainably fish different species so we can provide the necessary food resource for a growing population and do it in a sustainable way. How we can recreate responsibly with the ocean. How sometimes we unfortunately have the ocean get a little too close. So what can we do to be more resilient to impacts from storms? Understand that connection between the atmosphere and the ocean in that context. And then finally, a focus for tonight is how we understand how this dynamic ocean impacts offshore wind. So this is my laboratory. This is an animation made by NASA that shows that the ocean is just not one big blue blob of water. It has very complex processes like the atmosphere, right? The atmosphere has fronts and eddies. Well, the ocean has the same thing. And so here you can see the Gulf Stream making its way up the east coast of the US. It spins off into these eddies. And as we get even closer, there's more complicated things that go on as we consider all the fresh water that's coming out of these different estuaries. And so this is our challenge, is to try and understand the ocean as you see it here so that we can bring that knowledge to a planning process that'll consider something being offshore for decades. So these are the tools that we use. We have been at Rutgers working for over, well, this is our 30th anniversary. So for 30 years, come this October, we have been developing different technologies that allow us to observe this complicated ocean in a way that we can get continuous data from day to day, year to year, month to month, all of those important timescales. And each one of these circles is a different technology. We use satellites to give us maps of ocean conditions, networks of high-frequency radar systems to let us know where the warm water is moving, networks of buoys, drifters, which are telling us what the currents are doing as they move around subject to the currents, gliders, which I'm going to speak to at length here, weather stations, and all of this gets fed into a model. So just like you may be using a forecast to know that, yes, we had some warm weather today, but come Saturday, I think winter's right back at our face. Well, we want to try and do the same thing in the ocean. And so we're using these technologies. We bring that together in our lab on campus, where we can have all of the information about the ocean right now fed into a forecast, so we can start to see what the ocean's going to be like tomorrow, what it might be like Saturday or Sunday, and working with other groups that are trying to figure out what's the ocean going to look like in 2030, 2050. Really hard questions, but all data informed. And we use this space to bring all this different data together. These are our students who are interacting with that data. They're part of this observing system. And it serves many needs, from Coast Guard search and rescue to fisheries research that'll inform stock assessments and quotas for different fish, to monitoring for water quality along our coast. And today I'll give a couple examples of how we use this for offshore wind. The star that I'd like to introduce you to of this whole system is our underwater robots. As Caitlin mentioned at the start, we have a robot deployed right now off our coast. So I can be here virtually talking to you about the work that we're doing while a robot is out offshore in that weather collecting important data for us. So these are our underwater gliders. They're about the size of a person, you can see there. They are completely autonomous, meaning there's no one actively navigating these gliders. We put them out and periodically they come to the surface. We give them commands and they go underwater and they follow those commands and then come back up and let us know how they did. I often equate it to my teenage son. You know, we hope that they call in, we give them some good instructions, and you kind of let them go and see what they're going to do. These gliders behave in a similar way. Actually, often they're more reliable. They call back pretty much every time you want them to. So here's how it works. This is a diagram that shows the way the glider works. It doesn't have a propeller. The way that it moves through the ocean is it pulls in about a cup of seawater into the nose. That makes the glider heavy, so it starts to sink. But as it sinks, it kind of coasts down towards the bottom, just like riding on a bicycle and you coast down a hill without having to pedal. When it gets down to the bottom, it pushes that seawater out, and now it coasts up back to the surface. So we take advantage of the fact that the ocean is dense. So we can coast down towards the bottom and we can coast back up towards the top. And all the while it's coasting, it's not using energy to propel itself as if it had a propeller. So it can stay out for a long period of time. We have most of our gliders patrolling the waters where they're deployed for about a month. Other gliders are configured to last much longer. We've had the longest mission that we've flown with a glider is over 400 days, going from Brazil to South Africa. Every once in a while, in most cases, about every 2 hours or so, the glider comes all the way up to the surface. It sticks its tail out of the water, kind of like what's on my picture behind me, sitting at the surface, and it transmits its data back. And we can fill in all of those up and down motions to fill in what the ocean looked like in that section of data. And depending on the mission, we have specific sensors we can put on the robot. So we can measure things like water temperature, water salinity. We can measure things like phytoplankton concentration. So how much plants, what's the concentration of plants in the ocean? We can measure things like active acoustics, kind of like a fish finder on a boat. Well, we can put that on the glider, so we can map schools of fish. We can also put hydrophones on the glider, so we can listen for animals that make noise, like marine mammals, different whale species, dolphin species, and even some fish. So we have a lot of flexibility in how we can use these robots. And we at Rutgers have been using these robots since 1998. We've deployed them all over the world. We focus a lot off the coast of New Jersey, but you can see there are many different types of missions, from focusing on very coastal locations, either in the poles or in the tropics, to sending gliders across ocean basins. This was our 400-day mission going from Brazil to South Africa. And so it's a really useful tool for us as oceanographers, because we can put them out in some harsh conditions, whether it's a lot of ice, whether it's hurricanes, whether it's just regular nor'easters. The nor'easter that we had last week, the glider was making those measurements so we can see what the ocean is like. And it overlaps a lot with offshore wind. So here's a zoomed in map of the New Jersey coast. You can see the different wind energy areas in green, and all the different locations. This is just since 2015. I didn't put all of the missions since 1998. It'd be hard to see anything other than a lot of black spaghetti. But these are all the different missions that have been flown since 2015, and it overlaps with that wind energy area. So there are data, 20 plus years of data, that we can use to understand what the ocean is like now, that can be used to help inform offshore wind. One of those ways that we're doing it, these are some of the concerns and priorities that have been raised from the fishing industry, and I'm going to focus on just a couple. There are other ways in which we're using them, and I'm happy to answer any questions about that, but I just wanted to give a couple examples to give a sense of how we're using these robots. They've raised issues about understanding how access might be impacted, how navigation and safety might be impacted, but I'm going to focus on the ecological impacts. That's where my research goes in. And there's been questions about what impact these turbines might have on physical ocean processes and then related biological ocean processes. And there's been mention of this thing called the cold pool and what impact it might have on the cold pool. Well, our gliders are well suited to understand that. For those that aren't familiar with the cold pool, that's literally a mass of very cold water that persists through the summer off the coast of New Jersey. So what I'm showing here is water depth. So it's going from the surface down to the bottom. And as you move from left to right, we're going from the beach offshore towards the canyons. And so what you see is the ocean gradually gets deeper as you move away from the beach. And the colors here represent temperature. And this is a summer data set. And so what we see is really warm water at the surface. These are temperatures that are, in that 70s to 80 that we're kind of accustomed to when we go to the beach in the summer. But just below that, about 40 feet down, is cold water where this is in the 40s and 50s. And this is cold water from the winter before that stays there through the summer. And there are a lot of fish species that rely on that. And so this is what that cold pool looks like. Here's a graphic that shows what it looks like through the region. And so you can see that it's literally this blob of cold water, and it has really important impacts on many of the fish in the region. And so the community has asked, well, what might wind turbines do to the cold pool? And so we were part of a report that went out where we said, to really answer that, these are kind of the questions that we need to know. First question is just, does the cold pool overlap with energy areas? That's fundamental number one. If there's no overlap, then there's no issue. If there's an overlap, then we need to understand if there's an issue. But that's the first question, is just, do they overlap? And then if they overlap, what level of stratification, which is basically how big a difference is the temperature from that warm surface to the cool bottom, is that temperature difference going to be impacted by wind turbines? And then the third is the cold pool's not there all year round. It forms in the spring when the days start to get longer, and it breaks down in the fall with many of the storms that we get in the fall. So how does this kind of change over time? And so these are some of the questions, and this graphic is kind of meant to show how we're addressing this. So the question related to this is, here's our cold pool, right? Here's our warm summer surface water that we like to swim in. And if you have a turbine there, currents go, there could be turbulence that comes off of that, and it might mix the cold pool with that warm surface. There's also a potential for the wind turbines to take a stronger wind, and since they're pulling energy from that wind field, and make it a weaker wind, which will then reduce the amount of current, which might reduce this mixing. And so it's a really complicated question. And the cold pool doesn't look the same when you go to the spring, to the summer, to the fall. And so we're using our gliders and all of this data to map the cold pool. And we've been doing this with all these deployments for many years. And so right now, we're starting to do that research to look at what that overlap is between the cold pool and these wind energy areas, and then understand how strong that temperature difference is, so we can start to answer some of these questions raised about what impact the wind farm might have on the cold pool. So the good news is we have these data, and we can use these data to inform those questions that have been raised. The last example I'm going to give is on marine mammals. The North Atlantic right whale in particular is a very threatened species. The latest numbers are somewhere between 350 and 400 individuals left on the planet, and they migrate through this region. And we want to understand when and how they migrate, so that any human activity that occurs offshore will not adversely impact these whales. And there are already human activities that do that, with either vessel strikes, sometimes with loose fishing gear and things like that. So we're already, as a community, trying to figure out how we can change some of the things that we're doing so we don't impact the whales as much, so that they can recover. But certainly when we introduce something like offshore wind, we need to understand more about these whales, so we can figure out, well, will construction activities impact them? And right now, many of the ways in which these impacts are minimized is by having trained people called spotters with binoculars on the vessels doing the work, and they're looking out for these whales. And if they spot the whales in the area, they will cease work, or they might employ some other mitigation to minimize the impact on those whales. Well, what if we were to put listening devices on our robots and have our robot gliders patrol the areas, or put them on buoys in the areas? And so we're working on projects to test that question. Could we listen for those whales and let the robots come to the surface and tell us, hey, I just heard a right whale over here, or I just heard a humpback whale, so that that can inform how different steps of the offshore wind development process happen. And could it be done more efficiently and at lower cost? So we've started with a project called EcoPam. It's funded by Ørsted and the Ocean Wind facility. And it's a project in which we're partnering with the University of Rhode Island and Woods Hole Oceanographic to test that very question, putting hydrophones on our glider and on moored buoys to see how that might inform the way Ørsted, in this case, is developing their ocean wind project. So this is what we've done so far. We've completed 5 deployments off the coast of New Jersey. Each one of these squiggles is a different deployment. I mentioned we have one underway, and I'm going to show you that one. And we have 2 additional ones to plan for the remainder of this year. And what this allows us to do is this sensor right here is our hydrophone. So that's what's listening for the whales. But we also have sensors on here that measure the ocean. So here's an example from one deployment. Again, this top part is the surface. And the black here in this case is the seafloor. So you can see we started out near the beach. We kind of went offshore a little bit, then we came back towards the beach, and then we went back out all the way to the canyons and then came back in. And the color in this case is temperature. So we can see that warmer water. Here's our cold pool right here. This is that same section, but now we're looking at salinity. So the yellows are saltier water and the blues are fresher water. And this is a measure of dissolved oxygen. So we have higher oxygen concentrations in the surface and lower oxygen concentrations in our cold pool. And each one of these red marks is where we heard from whales. And so what this allows us to do is we can start to see if there are particular ocean conditions that we find more whale detections and other conditions where we find less. And so we can start to understand with a tool like a glider, both the oceanography and the ecology of the whales at the same time to try and get a better understanding of their habitat. And this is our glider that's out right now. So we deployed it on January 13th. It's still out. We're going to keep it out probably through next week. And these are the detections of right whale, fin whale, and fish over the course of the mission. And this right here is where the glider is now. And we've been hearing from fin whales almost throughout the entire mission. We've heard from right whales in certain locations, and we're mostly hearing from our fish near shore for this particular glider. And so this is an example, and I'm going to show you if this works. Can you still see my screen, Caitlin?
Yes, we can still see.
Okay, perfect. So I went to our website, and this is a map of that glider.
Actually, I think we can see, but I don't think we're seeing the screen that you're showing.
Oh.
We still see the presentation.
Oh, well, that's not good. Let me see if I can fix that. Let's try this.
There we go.
Yes?
Yep.
Okay, perfect. So this is a map showing the location of the glider. And here you can see this is where it was when it called in. If I drop this down, this is on our website. We can see that it last surfaced. In this case here, we're 2022, February 3rd. And this is 2300 in GMT. So we take, I always forget, is it 4 or 5 hours right now? I can never remember. Well, we can figure that out. Let me go here. So it called in 19 minutes ago. So at this, a little bit before, during this presentation, the glider called in and it told us where it was. And this is an example of the data that we're getting in real time. So here, for example, is temperature. Again, this is water depth. So here's deeper data, and this is up near the surface. The color in this case is temperature. And this right here, this deep purple, is 3 degrees Celsius. So 3 degrees Celsius is around 36 degrees Fahrenheit. And this was our nor'easter last week. So it got really cold. And so this is an example of some of that data as it's coming in, and what we're finding, and I don't have the plot made yet because it's hot off the presses, but what we're finding is that a lot of these whale detections for right whales are occurring near these temperature fronts. So where it goes from warmer to colder water or from colder to warmer water, we're seeing more and more of these whales. So it's allowing us to get a better sense of how these whales might be migrating through the area. Using some of these fronts. And let me go here. Can you see my presentation again?
Yep, you're good.
Perfect. Okay. So this is an example. Here are two locations where we saw detections of right whales. And that's the same map over here. These are two circles are where we saw the right whales. And this is a map of where the ocean fronts occur. And so we can see that these particular detections occurred near this front. And that's particularly exciting because if we get enough data that supports that this is a real thing, then we'll have some way to basically map greater risk of encountering right whales because we know where these fronts are because our gliders are out there. And so we can provide greater guidance to the wind developers and to the regulation and all of the different groups that are in need of these data. These robots can provide that for us. And so I'll finish by just saying that offshore wind is coming. There's quite a bit of activity, and our role is to make sure that the complexity of the ocean and all the stakeholders that have expertise in this area are contributing and being part of that development system, so it's done in a responsible way. And Rutgers, in particular, the role that I've been playing with a lot of my colleagues has been to see how we can take that more complex physical and biological ocean and provide the relevant science so that it can be implemented in the best way. And I am more than happy to take questions. I leave my contact information here as well if you're interested in learning more about what we're doing at Rutgers. And I'll finish there, Caitlin.
Awesome. Thank you so much. That was fantastic. And there were some really great like visuals and simulations that you used that really communicated the research really well. So that was so cool to watch. And as you were explaining it, really, really great visuals. So thank you for that. That was really cool.
Sure, happy to do it.
I have a question. I have a couple of questions actually. I don't see anything in the chat right now, but for anyone that does have a question, feel free to pop it in. Does the general public have access to your glider data that you showed?
Yes, all of the data that we collect with our gliders is available through our website, but we also send the data to, for example, we send it to NOAA. One of the other key applications we use for the data is storms. So the Hurricane Center uses our data so that they can get a better idea of what the ocean temperatures are beneath tracks of storms as they approach our coast. We provide the data to the Coast Guard so that they can use the data to inform how they might conduct a search for someone in distress at sea. So all of the data is public, and there's a variety of ways the public can access it.
Cool, great. I think I actually just found what you had up there. Let me know if that's it. Are you cool? Data gliders. So
yes,
yeah, if anyone's interested, I know we have a few teachers that joined us tonight. So really super cool to review with your students. So thank you for sharing that too. So I have a question about how far away can the glider pick up sound from the marine mammals? I know sound can travel pretty far underwater. So does it give you a range of that while it's listening?
Yeah, so it depends on many factors. Mainly the factors are how much background noise there is. So in a place like the New Jersey coast, there's a lot of shipping activity and things like that. So if we're near the shipping lanes, the range will be reduced. There's also, it depends on the species. So some whales use lower frequencies, which travel further than higher frequencies. But on average, it's about 2 to 3 miles. And that can obviously change, but if we're, if it was a ballpark question, that's the ballpark. It's about 2 to 3 miles from the glider. The whale
Gotcha.
really needs to be to hear it.
Okay. All right, there's 3 questions in the chat. Why are right whales particularly in focus? Software being used, and is New Jersey putting any attention to floating platforms? That's an interesting question.
Yeah, great questions. So there are many species that are being considered. I gave one example on the right whale because the right whale in particular is the most threatened. It's the most critically endangered. But there are considerations for, you saw we were also monitoring for humpbacks, sei whales, and fin whales. But there is research ongoing and monitoring going for different fish species, different other marine mammals, sea turtles, even different birds and bat species. So all of those different members of the ecosystem are being considered in this. In terms of software, so there's a lot of different software that's being used. I'm a bit of a dinosaur in our lab, so I still use a software package called MATLAB, which is not great for public use because it has licensing, but Rutgers has a license, so that's something we use. But I would say most of the processing that's being done now is being done in a Python environment, if that's familiar to you, Chris, and also R, the R Studio package, which is a statistical package. A lot of development being done with software. And then the question about offshore floating platforms. So that has been more of a focus off the west coast of the US and in the Gulf of Maine further north. And the reason is the ocean gets deeper much faster in those parts of the country. So one of the benefits from an engineering perspective is that the ocean off our coast gets deep very slowly as you move offshore. It has a relatively wide continental shelf. And so for that reason, in terms of costs and engineering, it's more feasible to do monopiles or jacket type foundations that are anchored to the seafloor.
All right, great. And then a couple of questions from Christine. How do you measure plankton or phytoplankton? Is it chlorophyll? And a couple other questions, but I'll stop there for now.
Yeah, the phytoplankton, you're exactly right. It's measured by estimating how much chlorophyll is in the water. And we do that using a sensor called a fluorometer. And that's because we can actually send out, the glider sends out little pulses of light that are at the wavelengths that we know chlorophyll absorbs light in the photosynthetic process. And one of the processes that occurs when phytoplankton chlorophyll absorbs light is it releases light at a different wavelength. And that's exactly what the glider does. So it sends light out at one wavelength, and then it detects light at the other wavelength. And the only thing that could cause that light to return at a different wavelength is chlorophyll. So that's what it uses to determine how much phytoplankton, or estimate how much phytoplankton is in the water.
That's really, really cool. And then what do sunfish sound like? Do they make a noise?
Sunfish, the boat or the fish? Yeah, I don't know. So that's my back. I work with fisheries folks, and so I'd have to ask them. But there are quite a few fish that do make noise, and those noises can be detected. So most of the species that we are focusing on with this glider right now are the marine mammals, which are much more vocal, but we do detect other fish that are making noise.
Is it possible for the gliders to interfere with species, like, bump into a school of fish or a marine mammal, or can it like detect it and move out of the way and then get back on course? Does it ever, get thrown off course from interactions with wildlife, or?
Yeah, good question. So the gliders move really, really slowly. Most babies crawl faster than our gliders swim through the ocean. So our gliders go at about half a mile an hour. That's the speed. So most of those animals are avoiding the robots as they move around, and they're neutrally buoyant. So they're not, they're literally just nudging up to whatever they might come in contact with. Now, we have had interactions with wildlife. We've had remora, which are the fish that stick themselves to the underside of sharks. They will stick themselves to the underside of a glider, hoping to get a meal. And they realize eventually that the glider is not going to provide them any meals, so they kind of leave it be. We've also had interactions with sharks. We've recovered gliders with shark teeth sticking out of them. And we had one interaction in the Antarctic with a leopard seal.
Oh, wow.
And the mystery one is we were in the Indian Ocean, and at about, 1,500 feet deep, the glider was basically jostled around for about an hour. And when we recovered it, it had suction marks on it. So we're pretty sure some sort of giant or colossal squid got a hold of the glider.
Wow, that's crazy, but really fascinating. One other question from Christine. How much does the Ørsted wind farm overlap with that cold pool that you mentioned?
Yeah, we don't know the answer to that yet. That's what we're working on to quantify exactly how and when it overlaps. My intuition is that a majority of the time it likely is offshore, further away from the coast than where those wind farms are planned, but we have to do the analysis to see. So that's still under research right now. We have a student actually who's working on that as part of her thesis right now.
Great, yeah. All right, and then it looks like we have a question about how far offshore do the leases start and how many wind generators are planned?
Yeah, good questions, Bob. I believe, and I had to check my math, I believe the lease areas off southern New Jersey, the closest I think are about 12 miles, and it extends as far as 22 miles offshore. I think it's something in that ballpark. Don't quote me on that, but it's in that range. And in terms of how many wind generators are planned, yes, it's as easy as doing that math. So if you take 7,500 and divide it by 12, that's how many wind farms would be, or how many wind turbines would be needed. Now, not all of those have to be directly off the New Jersey coast, and that's where that transmission that I mentioned, the research is going in terms of how wind farms that are further south or further north can also provide power towards that goal. But if you want a rough number, that's the rough number. And I will say some of the manufacturers of the wind turbines are developing individual turbines that could be as high capacity as 15 megawatts or even higher. So as the technology continues to evolve, the turbines themselves get bigger, but then it requires less turbines to get the same amount of power. And the number that I was given for the 12 megawatt turbine, one rotation of the turbine will power an average home in New Jersey for 2 days.
Wow. All right, looks like we have time probably for one more question from Chris. Is Ocean Wind one the furthest project in development in New Jersey right now?
Yeah, so New Jersey has so far, I don't know what the right word, they have these solicitations, and Ocean Wind was the first, and it's the furthest along. And then there's 2 other projects that are about a year to 2 years behind Ocean Wind, and that's Ocean Wind 2, as well as the Atlantic Shores project, which I'm not sure if it has a particular name, but those are the schedules. And my understanding is that Ocean Wind 1 is scheduled right now to start construction in a little over 2 years from now.
Okay, gotcha. All right, well, I think that's it for this evening. Josh, I wanted to thank you again so much for that presentation. It was extremely informative, really, really interesting. You know, do you have any more deployments soon after this one, after you take it out, or is it kind of done for a little while?
No, we're gonna recover it right now. This time of year, it's all about finding weather windows to get out there. You're all aware of how crazy the weather has been, and so we try and find a safe time to go out there and get the glider. But our plan is to charge. It just gets charged overnight. We plug it in, charge it up overnight, and then we send it back out. So it's going to go almost immediately back out after we recover it. So we're going to try and be pretty continuous out there through the end of March.
All right, sounds good. Well, thank you again so much for this presentation, and thanks for your time. Thanks everybody for tuning in tonight. Awesome questions, and we'll have this up, recording up within the next day or so as well. So you can rewatch it or share it with a friend if you'd like. But I will let everybody go, and enjoy the rest of your evening, everyone. Thank you so much again.
Yeah, thank you, everyone. Thank you, Caitlin, for the invitation. This was great.
Oh, yeah, sure. Absolutely. Thanks for your time again.